All right, so today we're going to talk about impulse. So impulse, remember how velocity is like the change in position over time, and then the change in velocity is acceleration. Well, momentum is like the measurement of the velocity times the mass. Well, impulse is kind of like the mass times the acceleration. And so what that's used for, and it's basically the change in momentum. All right. So we're going to talk about momentum, and then impulse is the amount of change in momentum. So write this down, which is a little confusing, but I'm not confused because I learned this. But when I learned this, it was a little confusing. So what letter do we use for impulse? Clearly, we're going to use, J, right? So can somebody get that? So this is the impulse, okay? And really remember that that is the change in momentum, okay? And there's two ways to calculate it. One way is to, just that right there, thank you. One way to do that is to do the force applied to an object over time. Which works out from a dimensional analysis perspective the same as the change in momentum. So the other way to do that is, remember this is the change in momentum, so change in P is equal to P final minus P initial. And usually the mass doesn't change, so it would be a change in velocity. So it would be the mass times the velocity final minus the mass initial final. Okay. So that's two ways to do it. And by the way, the change in, this is an interesting thing. I don't know if you guys are aware of this, but what is this? Final minus the initial. Well, that's delta V, right? Just kind of reviewing some things. So it's really the change in velocity is what we're looking at. Okay. So another way you could think of this too is J is equal to the mass of the object times delta V. This one is not as common for some reason. All right. Does everybody have this written down? Or do you need a second? I can wait. We need a signal. What's that? Sorry, I couldn't hear you. You had your earbuds in. We could do like a thumbs up. That's very elementary school, right? Is everybody ready? Okay, good. Can we go? All right. So as I mentioned in the previous slide, the change in momentum really has an impact on like the change in velocity because the mass never really changes. So that doesn't always mean that you're always increasing in speed. Sometimes you're slowing down. So here we have a car, right? And that car has a momentum. What is the momentum? Well, the momentum is the velocity times the mass. So when we think of this car, and you need to write all this down. When you think of this car, And we'll assume that it's 2,000 kilograms is the mass of the car. And it's going at 10 meters per second, okay? And then it has to slow down to stop at a stop sign. So when it stops at a stop sign, the momentum is 0. And so the change in momentum is the final momentum minus the initial momentum. And so because this has to deal with acceleration, there are a lot of similarities in the acceleration. So because I'm slowing down, my change in momentum is negative. Okay, does that make sense? My momentum is going in the opposite direction of the car. We're slowing down. We're not speeding up. And so when you think about that, if we're slowing down and we're not speeding up, that's a type of acceleration. And usually it opposes the motion, so that would be a negative acceleration if the car is moving in the positive direction. Okay. But momentum really is a measurement of the resistance to change, right? So it's not just about velocity and acceleration. The more massive the object is, the more momentum is required to either move it or to slow it down because it's more massive. So it's the product of the two, right? And then if you think about that, remember that your momentum, the impulse, is the change in momentum, which is also equal to the force, right, times the time. So the more massive an object is, the more force you would need to slow it down. So if that was a school bus and it was 5,000 kilograms, we'd need a lot more force to slow it down. And the change in momentum would be greater, right? And we need to figure out how long it takes for it to slow down. Also, another thing not to forget about is the velocity. So if you think of something very tiny that travels fast, like a bullet, bullets have a lot of velocity. They go pretty darn fast, but they don't have very much mass. So I was having a discussion with the other ICP physics teacher, and we were talking. He said that he had a homework problem where they were talking about the momentum of a bullet versus the momentum of a structure, like target practice or something. And basically, because the structure was way more massive, it didn't matter how fast the bullet was going. It barely moved it. The object that it impacted. So we were just having a conversation about that. So did everybody have this written down? Or are you just stretching, putting on your shirt? Okay. All right. So the change in momentum is called impulse, right? And I know that some of these slides are repeating themselves, but that's okay. I gotta get it in your brain. Since impulse is the change in momentum, and I'm going to show you something here real quick that we'll add on. And remember, it's the mass times the velocity, right? So that's where that comes from, is mass times velocity, the units. And you said, but Mr. Adams, you also said that it's the force times time. Well, what is force? Well, force is a mass, right, times acceleration. Remember that? Force equals ma. And then times time. Well, when we talk about the units of that, the mass is kilograms. The acceleration is meters per second squared, and then time is just seconds. One of these is going to cancel with one of these, so then my final answer is going to be kilogram meters per second. That's why that works. So a cool thing about physics is if you know what the units are, Sometimes you could try different things. And it just makes sense too, because the change in velocity is just acceleration. And it makes sense that you would somehow measure the time that it takes to change the velocity. All right, does everybody have this one written down? So let's do a problem together. It says, what is the change in momentum? Well, I have a car that's 1,000 kilograms that's initially parked. What does that initially parked tell you? What's the clue they're giving you? All right, it's early in the morning. That's okay. What were you going to say? Yeah, it's at rest, or the initial velocity is 0, right? And it accelerates to this speed, 15 meters per second. So that's the final velocity, 15 meters per second. All right, so remember that the change in momentum is P final minus P initial, or the mass of the car times the velocity final minus the mass of the car times the initial final. Now you can simplify that and just say the mass. You can factor out the mass and just say final minus initial velocity. The math works out the same. Okay? But because the initial is 0, it's really just the mass times the final velocity. This whole thing goes to 0. Because anything times 0 is 0. So then my change in momentum is equal to 1,000 kilograms times 15 meters per second. Or 15,000 kilogram meters per second. So that's the change in momentum. Okay? Does everybody have that written down? All right. So then what is the impulse? It's the same. The impulse is the change in momentum. Okay? That's the word we use for change in momentum. So if you think of a roller coaster that's on a roller coaster ride, because it's constantly changing its velocity, and remember, velocity is a vector, so not only is it changing its velocity by going up and down the hills and speeding up and slowing down, but when it goes through a loop-de-loop, it changes its direction too. Okay? But we're just going to focus on linear momentum right now. Does everybody have this written down? Okay. All right, write all this out, draw the picture. It says a 500-gram ball of clay is falling at -2 meters per second when it strikes the ground. Okay, so it sticks to the ground without bouncing. Now that's important, because when we start to talk about collisions next time, and we talk about the conservation of momentum, that's kind of an important thing. Okay? So what does that mean? What is the impulse of the clay? Well, let's unpack this. 500 grams is 0.500 kilograms. We need to have it in kilograms. The initial velocity is -2 meters per second. What's the final velocity when it hits the ground? Well, it's 0. It's not moving anymore. So remember that impulse, letter J, makes perfect sense, is equal to the change in momentum, which is equal to the mass times the final velocity minus the initial velocity. Now this is very important. It says watch out for signs. They're letting us know that this minus sign and then this minus sign are going to do something. Whoops. So what does that mean? Well, the mass is 0.500 kilograms. My final velocity is 0 minus my initial velocity, which is also negative meters per second. Okay? So when you minus a minus, what happens? Yeah, it becomes a plus. What's 1/2 of 2? That's our final answer. 1 kilogram meters per second positive. It opposes the direction. Why? Because the ball stops. Does everybody have that written down? So there's a little bit nicer handwriting there. Now the ball, because it's clay, it's going to deform a little bit. It's absorbing some of that energy. All right, now let's see what happens when the ball bounces back. So same type of question. You want to write out some of the things. Sketch out this drawing, though. So it says that 500-gram super ball is falling at 2 meters per second. So that is the initial velocity of -2 meters per second. Why? Because we're going to say that falling is negative and going up is positive. When it strikes the ground, it bounces back, which is the final velocity of 2 meters per second, because it's positive, right? Will the impulse of the super ball be greater or less than the impulse of the clay? Well, let's see. Impulse is the change in momentum, which is equal to the mass times the final velocity minus the initial velocity. Again, this is going to be 0.5 kilograms. So I'm going to say 0.5 kilograms. And then I'm going to have 2 minus minus 2. When you minus a minus, it becomes a plus. So we really have 0.5 times 4. That's a point right there, I'm trying to make a point, but it keeps goofing off. There we go. What's 1/2 of 4? +2. Oops, I forgot my kilograms. You guys should be writing this down. It will help you with your homework today. Okay. So that's greater, isn't it? It's double. And so we would call this elastic. So elastic means that it doesn't stick. We would say it's elastic. The other part where the clay sticks to the thing here, when we go back here, that would be inelastic. But here, this is what we call elastic, and I think I misspelled the word elastic. There's really only one L. It's really hard to do this writing and talking and recording all at once. Don't you guys feel sorry for me? No? Okay. All right, so that's the same math that I had before. You don't have to write all this down. Just kind of look up at the screen and we'll talk about this. So there are many ways to deliver the same impulse. Here are 3 ways to apply an impulse to slow down a car. I just looked at the pictures. In each case, the impulse J is equal to the change in momentum, or delta P, is the same. What is different? So 3 different ways. You apply the brakes slowly, just slow down the car to come to a stop sign. You could slam on the brakes, right? Or you could hit a brick wall, right? Notice the car, these are very accurate descriptions of the car. In this one, the car just seems to slow down. This one, you slam on the brakes abruptly, the car kind of wants to keep going forward, because momentum is a measurement of kind of inertia, right? Like, or they're not exactly the same, but it determines, it indicates how much something wants to keep going once it's going, and how much it wants to stay still once it's still. Hitting a brick wall, you do damage to the car. Now, the difference between those is the amount of time that it takes, right? So the time the impulse is implied is different in each case. If the time decreases, the force must increase, right? Because it's the same amount of change in momentum or impulse. So if you don't want a lot of force, you need to have a longer period of time. Does that make sense? So remember that the force exerted for a time, write this down, delta T applies to the impulse J. So J is equal to the force over time, which is also equal to the momentum or change in momentum P. Okay, and it's the same units. It's the same units. And I showed you that on the other slide, right? So Newton seconds is the same as kilogram meters per second. All right, I'm going to skip a couple things. Again, you don't have to write this down. I just want you to look and see what happens here. You could change an object's momentum. To change an object's momentum, you can apply a large force for a short time or a small force for a long time. So when my son was in the 6th grade, he participated in Science Olympiad, and we did the egg drop. And so I wanted him to win, so I said, well, in order for the egg not to break, we just need to increase the time that it takes for the egg to slow down. Most 6th graders think that way. So I actually, and you had to put it, I don't know if you guys have ever done this before, but you put it in a milk carton, and then you could do whatever you want inside the milk carton. So what I did is I put like foam rubber in the milk carton, and I also put little balloons that were filled with sand, and tied them to the 4 corners of the bottom because I wanted it to go down, and I think we tied a parachute to it too. But the egg could literally slide down, and there was a little bit of cotton at the bottom. So what I did for that egg drop, I'll kind of sketch it out. Inside, this is the carton. We had little balloons tied to each corner. And then, it's got the little thing on the top. I'm not even going to draw the top because I'll screw it up. But then we had like a parachute. And then on the inside of it, there was this kind of a gray, but we'll make it a dark blue, foam rubber. And then we placed the egg right here near the top. And then there was like cotton at the bottom. So what did that do? Well, it slowed down the impact. The egg, when it hit the ground, first of all, you needed the sand here for the weight. But what did the sand do when it was in the balloon? It would spread out. So that absorbed some of the force. It basically slowed down how much of an abrupt impact you had. The parachute also increased the time of the impact, or increased the time of the change in momentum. And then lastly, the egg could literally slide down. It could move a little bit. So I don't know about how long it took, but it really slowed down the egg. And so when we tested it, we could drop the egg from like, I don't know, 2 or 3 stories, and it would, every time it'd just go, and the egg would be fine. His teacher did say he came up with all this. And I was like, yeah, of course. But what happens is if you just fall and you hit the ground, your time is very small. But if you land on something, what it does is it slows down how long of the impact is. But it really what it does is it increases the time. You have to kind of squish into stuff. Okay? So this is an important thing for like collisions and sports collisions and stuff like that. Okay? Bumpers protect your cars. Now cars have crumple zones. And so what that's doing is it's just increasing the time for that change in momentum. That's why you have helmets with padding. The helmets, if you think about the material in a bicycle helmet or even a football helmet, it doesn't really, you know, it protects your head, but really the foam slows down, and that reduces stuff. Same with like football pads or shin guards and stuff like that. It just kind of slows down the impact. Okay, so let's do this problem together. Calculate the change in momentum of a car that is 1,000 kilograms, and it speeds up from 10 meters per second to 15 meters per second. So this is the initial velocity, 10 meters per second. This is the final velocity. I know my V looks like a U. We'll fix that in a second. 15 meters per, whoops, just going crazy. And this is obviously the mass. So the impulse, which is the same as the change in momentum, which is really the mass of the object, because the mass doesn't change, times the final velocity minus the initial velocity. So the mass is 1,000 kilograms. The final velocity is 15 meters per second minus the 10 meters per second. This becomes 5 meters per second. So isn't that 5 times 1,000, which would be 5,000 kilogram meters per second. Because 15 minus 10 is 5, right?